Good morning, everybody. I see that my two co-authors are also on. That's Joe Bindle and Jason Abbott. Jason helped with the laboratory setup, and Joe is, of course, head of the group that I'm in, and we do a variety of things across the spectrum of engineering and systems engineering work, but also a strong background in aerosol science and air testing and worker safety around air testing. So when the pandemic hit, um, we kind of came up with some ideas about ways that we might be able to contribute to the cause. We came up with the idea of looking at filtering of indoor air spaces. Um, for many of you, if you were active in you know whatever fields you're in at the time, it was difficult to obtain some of the equipment, such as HEPA filters, through commercial sources because they were being slurped up by hospitals and everybody along the way. So what we really focused on was what's called a homemade air cleaner. In other words, what could you make from commercially available off-the-shelf parts, but yet not a fully assembled device, and uh, and also looking at it as a simple thing you could do at home to help protect yourself in small businesses and small work areas. And so that's the notional idea of what we were pursuing here. And so in essence, a lot of indoor air spaces are not filtered. Some of the anecdotal stories from early in the pandemic were about people that were infected in indoor air spaces that were had poor circulation. And so this was an effort to look at all those kinds of topics. So, um, so the commercial air cleaners, such as in the first picture here, you can see they're uh, fairly expensive, in the consumer price world. In other words, somewhere $100 to $500. Um, they also have limited availability at times because a lot of people were having a run on them at the stores. Um, they can be very effective for certain types of pollutants and can be effective down to reducing virus-sized particles. Um, and so that was kind of the model that we were looking at, is what can be done to replicate that type of performance using simple homemade materials and parts. And then also, um, you know, what can MRI's role be in this? We can help lay out the components. We could also do some basic performance testing. We have an aerosol test chamber um, that Joe and I have used on numerous occasions for exactly these types of small particle tests, and offers a chance to again contribute to the greater cause for uh, and to show capabilities and possible business development in these areas. For any of the listeners, of course, I'll be glad to answer questions along the way, but I'll, uh, I will gladly continue as we go, and you all can join in whenever uh, you feel a need. So if we move on down to the lower left corner there, thank you, Tina. For most of the MRIGlobal employees, this is all going to be almost second nature. Not a lot of surprises because most of us have a pretty strong science background and an understanding of the way, kind of an intuitive, instinctive way of the way small particles and infectious diseases can spread. But this is just a nice background. Um, Again, as most of us know at this point, the COVID-19 coronavirus is transmitted primarily through air exhalation. Um, and when we look at it in a scientific technical sense, we can kind of split the particle sizes into two categories: the large droplets, which are larger than 5 micron, you know, they would carry a large amount of virus because the virus itself is only roughly on the order of a tenth of a micron particle size. So you can pack a lot of particles into a 5 micron droplet, in other words. But as a consequence, those droplets are also fairly heavy, and that's such as large breath particles. Okay, and that's where the social distancing comes in. Is again, most of those particles will fall out over about a 3 to 5 foot distance, and you can visualize that, of course, with you when you breathe on a cold day. You know, you can see your breath out to a certain distance. You know, when you fog a window at a certain distance away, that kind of thing. And in the laboratory and in the field tests, of course, Joe and I have seen these kinds of things many times with sampling particles, large particles that uh, after a relatively short distance, they just fall out of the air because they're so heavy. Um, so then another type of particle that is exhaled, then again, it would be the smaller particles or less than 5 micron. Now, these particles are airborne for a long period of time. They're inhaled deeply into the lungs and create more of a health hazard from the industrial hygiene standpoint. For example, you hear about things like PM 2.5, PM2, you know, PM1, the small particles, very small particles that are regulated by OSHA and EPA for worker hazard, such as asbestos and fine dust. And they're regulated because of those same reasons, because they are they remain airborne for very long periods of time and are inhaled deeply into the lungs. So with a with a virus, the particles that are very small, that are not conglomerated into the large particles, they would remain airborne. And basically, the ways you can mitigate that is through HEPA filtering, you know, through your operating your HVAC system, through uh, you know, being outdoors so that you know, the wind currents in the large area can absorb that kind of particle into the greater area. Um, so basically, what we wanted to do was replicate the behavior of the very small particles, and so um, Joe's got a wealth of experience at aerosol testing and helped us work through how to set up some laboratory testing using small particles with a particle generator. We'll get to that in just a minute, using a material called ovalbumin in order to generate that. And that's the crux of what we were going to be doing for these tests. So if we move across and then up to the top, we say, okay, how are we going to build an air cleaner? This is again what we're after, is making something that's very cheap and affordable for many people, an average citizen that wanted to do something to improve their defense against uh, infection in a unfiltered, uncirculated area. You can get a box fan for less than 20 bucks. You can get a very good high quality Filtrete filter for less than 20 bucks. And of course the old duct tape. And then from that, you can assemble a very simple thing there, like you see on the right, which is just simply duct taping to make a good air seal around it. And then you've got yourself a portable air cleaner. And we made several of them at our house, and we made some for my two oldest daughters to take with them while they went off to school. They used them in their dorm rooms. Uh, they they found that they also help a lot with just you know, general uh, allergies and indoor air quality in their rooms. But from that, that leads us to then, what is our test setup for what we're doing for this particular demonstration? And yeah, thank you, Tina. You're right with me. We're looking at the lower part. Um, for those of you that are not familiar with it, MRIGlobal has a fairly large walk-in aerosol test chamber. It's located across the hall from where word processing is, graphics. Um, and then we've used that chamber extensively over the last 3 to 4 years. We've done a lot of aerosol testing work for LivaNova, and and then use that same type of setup for this test. And what we have that we actually built a chamber within the chamber, so that makes it a little easier to keep clean and to keep the controls operating on it. So we have an inner chamber that has an 18 meter cubic meter volume, roughly dimensions then of 10 feet by 8 feet, 7.5 feet tall. So it's a full walk-in chamber, lots of room for fairly significant sized equipment. The inner chamber has its own set of HEPA blowers with exhausts and inlet air that is controlled by setting the fan speed on the HEPA blowers. So within the limits of those controls, we can control the air change rate within that chamber. Um, and so, for example, hospitals and different areas have certain types of air change rates that they are designed to. But you can also look then at if those filters are not being used, if those fans are off, then that would simulate an uncirculated room, such as some of the areas, again, that there's a lot of anecdotal stories about people being infected, like the mass choir infected, where they were in an uncirculated area and one person in the choir had the disease and spread it to everyone else. So that's the gist of what we were looking for. We generated our aerosols using what, for those of us who work with aerosol testing, is a standard piece of equipment, the Collison nebulizer. There's a picture of it there, as well as a graphic illustration of it spraying um, into the air. So we set the aerosolization to happen at breathing height, and then uh, uh, used a liquid suspension of albumin in water, and did some preliminary tests to demonstrate that that generates a range of particle sizes uh, down at the submicron size up through about 10 micron. And for these particular tests, we really focused on the small particles. Um, all these tests generated larger particles, but again, the larger particles will fall out of the air in a relatively short time period. And so we really focused at seeing what the kind of activity and dynamics are occurring with the very fine particles, the less than half micron size. And we monitored those concentrations with an APS, which is an aerodynamic particle sizer. That's a kind of a standard piece of equipment that's used for aerosol testing, and it monitors the full range up to 20 microns. So we were able to get a pretty good understanding of what's happening across the spectrum of particle sizes. Again, really focusing on the smallest size alone for this test. And then we placed the air cleaner in the middle of the room on the floor, and we'll start looking at some data here in a second here, but that's the crux of what the experimental setup was. And then up in the upper right, then you can see what kinds of tests did we do. Well, the first thing we wanted to do was show that we could generate a stable aerosol by doing the dissemination for about a 15-minute time period. And you can see in the plot, we've got a nice steady ramp from 0 up to something like 80,000 counts over a 15-minute time period. And then we would turn off the dissemination and just hold it, see how it maintains stability in the room to make sure, again, to visualize, are we having leaks or dropout that's unexpected? And you can see a nice plateau there over a 15-minute time period. So again, that illustrates how these very fine particles stay airborne and essentially maintain that air concentration during that dead time that we did. And then finally, after that 15-minute period is over there, that's you can see that's about minute 35 or 36 or something across on the chart, that we would then turn on the HEPA filters and begin the air change in the room at about 20 air changes an hour, which is a fairly high rate, but um, that concentration drops down real quick. So you can see we drop down from 35 to or at minute 35 or so to about minute 55. You can see you're knocking out almost everything on this particular scale. Anyway, it's a um, so that shows the performance of a HEPA filter. And a HEPA, for those of you that aren't familiar with, that's a high efficiency particulate filter. It's one of the most common filter types that's used in building design for when you're really looking at good quality air filtration. Okay, and so for our tests that we ran, we used two types of the box filters, the air cleaner off the shelf Filtrete 1500, which is rated for virus-sized particles. And we also used a slightly cheaper version, the Filtrete 1085, which is not rated for viruses. And we ran them at 3 different air speeds. We wanted to see, okay, well, what do we get? And really, we were impressed across the board here. Um, you can see the baseline HEPA filtration is the dark blue line. I'm sorry, that's kind of embedded. It's a little bit difficult to read because they're all so tight together. It's the middle blue line there in the down the middle of the chart. But what you can see from all of these are all put on the same scale, is that the Filtrete 1500 actually performs very well and actually outperforms the HEPA. Um, when you run it at a slightly slower speed, you get performance very similar to the HEPA, and in which you're getting essentially a 95% knockout of the small fine particles in about 10 to 12 minutes. So this is again a very small uncirculated room, the test chamber, 10 feet by 8 feet. So it's not going to work in a large auditorium. That's what your building HEPA filtration is for. But for small rooms where you're working in a situation that you can't control the air quality, uh, setting you can set this in between you and other people in the room, for example, and provide a certain level of assurance that you've greatly diminished your exposure to the virus. So the Filtrete, the cheaper grade, even performed very well. The 1085, not as well as the 1500, but you can still see for these very fine particles, it was a little surprising, but it still knocked out about 95% of the load over about a 20-minute time period. As the pandemic is lifting, some of this is maybe not as immediately relevant, but it's useful to know of, of simple tools that you can do that are affordable. And I was able to present some of this information to the city of Kansas City and some other folks in our contact circles through the pandemic, again, to illustrate our capability for performing these kinds of tests, developing good technique, uh, helping spread the word for what kinds of things an average citizen or a small nonprofit could do to help people out.